Hi everyone, my name is Sam Connerly, and today I'll be walking you through Physics 2212, Lab 2, Lines of Charge. So first, a little bit about the lab. It's about learning about the transfer of electrons through surfaces using tape, and evaluating the charge left on pieces of tape. This is going to be very similar to Lab 1, except with one key difference that we'll go over in a second. But first, going over a few details. First, we're going to assume that each tape has equal and equally distributed charges to start with. We're going to be using Newton's second law and Coulomb's law. And today in our lab, we're going to assume that the tape has charge uniformly distributed across its length. So there's one big new concept that we're going to go over, and it's about the electric field for a rod. We're going to treat the tape as a rod in order to calculate the uniformly distributed field. In our case, we're going to be acting as if we're observing from a centered perpendicular view of the tape. And because we're doing that, we'll be using the below formula for electric field of the rod. There is a formula that is used for when you're looking parallel to the rod. But as you can see, we're using the one that's perpendicular, and the formula for that is on the slide. Next. So the procedure, again, very similar as in Lab 1. We're going to create U-tape by attaching one piece to another, then removing. Place U-tape next to other suspended U-tape and observe the interactions between the two pieces of tape. Unfortunately, we do not actually have the materials to perform this experiment, so we are instead going to be using VPython to calculate the results of the experiment and show what the results would look like. And again, this is very similar to the procedure we used in Lab 1. So in order to do these calculations, first we need to have a few initial numbers and results. So tape length, we have 0.18 meters, tape width, 0.019 meters, tape surface area, 0.003 meters squared, the tape atom count, which is the surface area divided by the area of the atom, which we get about 3 times 10 to the 17th, as well as the electric charge on the tape, 1.2 e to the negative 8 coulombs, the tape deficiency, 7.5 e plus 10 e to the 10th electrons, distance between tape, 0.025, and weight, 0.02 newtons. So for the calculations in this experiment, we're going to be looking at the magnitude of the electric force in the tape, and that will be set equal to the magnitude of the force of gravity, which will keep the piece of tape suspended. So in order to calculate that, we'll have to set them equal to each other in order to solve for the charge of the tape. So the formula can be seen below: mass times gravity times our charge formula, and we'll be solving for Q. So let's go ahead and start looking at some of the coding that we're going to be performing for this experiment. This first slide just shows the initial setup where we're initializing those variables that we discussed on an earlier slide. Then we're going to be calculating the electric field and the line charge as well. This is going to be an iterative process across all of the different small segments of the tape. This kind of gives us an idea of how the charge changes as you move up and down the quote-unquote rod. And then we'll get a charge for the top tape and the bottom tape, and we'll be able to see the effects that they have on each other. And this can be seen as the setup that we're going to do in part 2, where we're actually going to evaluate the differences between the tape. This is going to show us where the bottom piece of tape is pushing the top piece of tape. As you can see in the printout below, we have a little depiction of what this looks like. As you can see, the charges kind of start to change direction as you move up and down the piece of tape, but they're all headed against the force of gravity in some capacity. And then we can see that when we solve for Q here, we get 2.4 times 10 to the negative 8 coulombs, and a deficient electron count of 1.5 times 10 to the negative 8 by dividing Q by the electron charge. And then I just wanted to show as an example kind of what we did last time so you understand the difference between the two calculations. Here you can see that it's just a point charge, and it's really just the charge going in one direction, kind of a simplification of the calculations. Sources for error similar to the last one. There are rounding errors, inaccurate measurements, as well as touching of tape during setup. And then discussion, what if we calculated like the previous model, kind of like we touched on earlier, the charge of the point charge calculations was less than that of the distributed charge that we did today. And also we can see that on a rod, the direction of the charges also slowly change, but it does not happen when we are looking at a point charge. Why does this change? Mainly because length considerations along the tape and the distributed charge along that length is being taken into account. We see that this is a more realistic model than the point charge model. That'll be it for the presentation. Thank you for joining.